All right, everyone. So, welcome to our second meeting of the Math 175 workshop. So, overall, in this workshop, I want to cover the limit definition of a derivative, finding the slope and the equation of a tangent line, and talk about basic derivative rules with you guys. So, in this first video here, I want to show you how to find the derivative of the following functions by using the limit definition of a derivative. So essentially, f prime of x is equal to the limit as h approaches 0 of the difference quotient. The difference quotient is given as f of x plus h minus f of x over h. Now, the examples that I choose in this for this problem, for this exercise, requires you to know how to compute limits analytically, right? Where you have to use some sort of factoring technique, talking about conjugates and the LCD methods to sort of simplify your limits. So with the first example, I'll do part A on this slide. It says f of x is equal to 3 minus 5x. So whenever I want to apply my limit definition of a derivative, the first thing that I have to do is first figure out what's my f of x plus h. To figure out what's my f of x plus h, all we got to do there is replace x by x plus h. So f of x plus h is going to be given as 3 minus 5 times x plus h. And we can just rewrite this. We could distribute the negative 5 inside the parentheses. This will give us 3 minus 5x minus 5h. Okay, now that you have your f of x plus h, you can now go ahead and solve the limit problem, right? So we say f prime of x is equal to the limit as h approaches 0 of f of x plus h. So the f of x plus h terms, I first like to place them inside a set of parentheses or brackets, minus the original function, 3 minus 5x, which also goes in a set of brackets. The reason why I do this is so that when we look at what's inside of the two separate brackets there, it's separated by a minus sign. So whatever terms they have in common, you can cancel it out. So what terms can I cancel out? 3 and 3 often, yes, you can cancel out your 3s and they're negative 5x. That's right. So you're reducing your limit. You have the limit now as h approaches 0. So just a quick tip here. Continue to write your limit statement as you're simplifying the expression, and then you evaluate your limit at the end. Okay, we have negative 5h over h. Now, can I reduce this further? Yes, as long as h is not equal to 0, your h's will cancel, and you will have the limit as h approaches 0 of negative 5. Now, what do you think this limit's going to be? As h approaches 0 of negative 5, what do you think your answer will be? Say it louder. It's going to be negative 5, right? Essentially, the limit as h approaches 0 of a constant function, negative 5, you can treat it as a constant function. It's just going to be your constant, so you get negative 5. And that is your derivative. F prime of x is negative 5. It makes sense, by the way, that f prime of x, or your derivative, is negative 5, because look at the original function. The original function was f of x equals 3 minus 5x. Now, do anybody know what does the graph of 3 minus 5x look like? Overall, what do you think Not necessarily a right side. I just want to know the overall shape. It's linear. There you go. It's linear. So therefore, it's a linear equation or linear function where the graph is a straight line. And one of the most important properties regarding straight line is the slope. What is my slope of this function? That's right. If you look at the original function, because it's linear, your slope is negative 5. And derivatives, by the way, as your professors probably pointed out to you in class, is just a fancy word, or yeah, it's a fancy word for slope. Okay, it's just a fancy word for slope. So f prime of x is equal to -5. Makes sense. If I give you any linear function and I ask you to find its derivative, it's always going to be the slope. However, when we move on to examples like parts B through D, that's no longer the case because these are not no longer going to be linear functions. All right. All right. Can we move on to part B? You have a question? Yeah, go ahead. We multiply the -5 by x times x plus h, but we don't multiply the 3 because it says 3 minus 5x, or sorry, 3 minus 5 times x plus h. Remember, this term, -5, listen closely, -5 is the term that you distribute inside the parentheses, not the 3. The 3 just comes along for the ride. Okay? Yeah? This one doesn't require FOIL, because in order for you to FOIL, you need to have something like, in quotes, x plus h times x plus h. In other words, you need an x squared term. We didn't have no x squared terms here, but in part B we do. Yeah?
I watched a YouTube video on this, and it said that I can do it in like a simpler way, using like shortcuts. So the 3, since it's a constant, it would be the 0.
No, we can't use that.
But not for everything.
No, absolutely not. It's a good thing that you pointed. So there are shortcuts to this. You will learn the rules, basic derivative rules, which I want to show you towards the ending, hopefully, of today's workshop. But if the problem says to use a limit definition, you use the limit definition. There's a problem on our final exam. There's a good question, by the way. There's a question that's on our final exam that states to use the limit definition, which is shown to you on screen in blue. If you don't use that limit definition and you use the derivative rules, you'll get that problem wrong. End of story. Okay? But don't get me wrong. You will eventually learn to use basic derivative rules, or you're going to learn a set of derivative rules. But for right now, no. You're just learning how to use a limit definition first. Okay? All right, let's look at part B now. Part B, we have g of x is equal to x squared plus 6x minus 7. So in this example now, again, your first thing is that you always want to compute the x plus h piece. Namely here, because our function name is g, we say that we want to compute g of x plus h. So wherever I see an x, I'm going to replace my x by x plus h. This will give us x plus h squared plus 6 times x plus h minus 7. What I want to show you here on screen is how to simplify this. So I won't do any shortcuts here. I'm going to show you algebraically how I personally expand this. So first thing is I rewrite x plus h squared as a product of x plus h times itself. And then I keep the other terms. I leave it alone for now. Now, since x plus h squared is x plus h times itself, I expand it using foiling. So if we FOIL this, you do x times x, which is x squared, x times h, which is xh. Hx is the same thing as xh, so I'm going to leave it as xh. And then lastly, we have h squared. Plus, bring down the rest of your terms. And now I could do, in this next line, all my simplification, combine like terms and do more expansion feed. So in our current line, it says x squared plus x times h plus x times h plus h squared. I can combine the x plus h's. If I combine the x plus h's, then we have 2 of them. So we say that it's x squared plus 2xh followed by h squared. Okay. And sorry. And we can expand the 6 times x plus h, which is 6x plus 6h minus 7. So that's your g of x plus h. Now that I have my g of x plus h, I can insert it into our formula for the derivative. We say g prime of x is equal to the limit as h approaches 0 of, well, the g of x plus h piece, this is just me personally, I like to keep these things in brackets. X squared plus 2xh plus h squared plus 6x plus 6h minus 7, close bracket, minus, open bracket, your original function. The x squared plus 6x minus 7, all divided by an h. Now, let's simplify this. Looking at the numerator, you will find that there's terms that are in common. Namely, the terms that you're finding in common are the terms of the original function, the x squares, the 6x, and the negative 7. So all the terms of the original function essentially goes away, and what we have remaining is terms that should have an h. So that's 2xh plus h squared plus 6h over h. So essentially from the difference quotient, I did the difference part, all right? Now we can do the quotient part. If you look at all the terms in the numerator, because they all have an h in it, you can factor an h out and cancel it with the h in the denominator, right? So this next line, I can write it as the limit as h approaches 0 of, factor out an h, you have 2x plus h plus 6, all divided by h. As h is not equal to 0, the h's will cancel, and your limit is simplified to be 2x plus h plus 6. As h goes to 0, you're just left with 2x plus 6. So now you'll see that when your derivative now, when your function is no longer a linear function, your derivative, in this case g prime of x, is actually a function. You have 2x plus 6. Any questions here with part B? Can I show you part C now? Okay, part C. Wait, go ahead. Because again, the function was x squared plus 6x minus 7. The very first thing that you want to compute when you're applying the limit definition of the derivative is the g of x plus h. Or, formally speaking, it's f of x plus h, but my function here named is g. So in order to compute g of x plus h, wherever you see an x in the original function, you must replace it with x plus h.
Is it the given formula?
It's in the formula, yes. Yeah. You could have rewrote our original formula as saying g prime of x was equal to the limit as h approaches 0 of g of x plus h minus g of x over h. It's part of the original formula.
Yeah.
I just did it. I only wrote the formula once at the beginning slide, but I never keep writing down. This is just workspace. All right. Okay. Can we continue? All right. So let's look at part C now. Part C's example says now we have a square root of x minus 7. So h of x is equal to square root x minus 7. Again, what is the first step I need to compute? We have to compute h of x plus h. So wherever I see an x, I'm replacing it by x plus h. The good thing is that there's only one x here. It's inside of the square root. So you just got to put a plus h there, yes. So you have x plus h minus 7. Now we apply our limit definition. It says that we take the limit as h approaches 0 of the square root of x plus h minus 7 minus the original function, which is the square root of x minus 7, all divided by h. Now, you've seen an example of computing these limits when you were computing limits analytically. Now, it's no longer essentially factoring technique that you're applying, but you're applying the conjugate pair, right? So remember, if you want to multiply by a conjugate pair, the conjugate, if you have a minus b to start with, to complete the conjugate pair, it's going to be a plus b. Right? This is your binomial, essentially, the square root of x plus h minus 7. We treat it as a single term, minus the square root of x minus 7. That's going to be your second term that you treat as a single term. That will be your b. So my a's and b's, I identify them. Since I have a minus here, to complete the conjugate pair, I multiply by the same thing with the exception of the minus sign becoming addition, right? We should have an addition sign here. So it's the square root of x plus h minus 7 plus the square root of x minus 7. And because we're dealing with a fraction, whatever you do on the top, you can do this on the bottom. So this is the square root of x plus h minus 7 plus the square root of x minus 7. All right. Now, the good thing about conjugate pairs, when you look at a minus b times a plus b, if you were to FOIL this out in the long run and simplify it, it just simply becomes a squared minus b squared, a difference of two perfect squares. So in the numerator, if I want to multiply or expand that out, all I got to do is just multiply the a terms by themselves, followed by multiplying the b terms. But since everything's since all the a terms and then all the b terms are under the square root, right? What happens when you multiply essentially the same square roots? What happens to your square roots? The square roots will cancel out. So this will give us the limit as h approaches 0, square root of x plus h minus 7 times itself is just going to be x plus h minus 7. And then you'll have minus the square root of x minus 7 times itself. So that will just give you x minus 7. And the denominator, you can leave it alone. All right, the denominator, just leave it alone for a moment. Okay, now things happen nicely for us. If you look at this numerator, I have x plus h minus 7, right? I'll keep that in brackets, actually, minus the original function, or just x minus 7. So we can cancel things out. What can we cancel? We can cancel out the x and the minus 7, right? The x will cancel out. The minus 7s will cancel out. So what will be remaining in the numerator? An h. So we have the limit as h approaches 0, h on the top, h on the bottom, times the square root of x plus h minus 7 plus the square root of x minus 7. All right, we're almost done. If you look at the numerator and the denominator, do they have anything in common? An h. So you can cancel the h out. If I cancel out my h, we make a statement saying h can be equal to 0, but more importantly, what will be remaining in the numerator? 1. A 1. Very good. So now I have this new limit, and I'll be able to solve this problem or find the derivative. The limit as h approaches 0 of 1 over the square root of x plus h minus 7 plus the square root of x minus 7. As h goes to 0 now, the h term goes away. So what we have in the denominator is the square root of x minus 7 plus the square root of x minus 7. You can combine this into a single radical because what we have underneath the radicals now are the same. So if you treat these as like variables or like radicals, we say that our answer is 1 over 2 times x minus 7, and that is our derivative. This is essentially my h prime of x. Okay, any questions with part C? Good? Wait, go ahead. Oh, you see, in the denominator here, we consider these as like radicals. So because they're like radicals, you can combine them as if, you have x plus x, or if you have y plus y. So how many copies of x minus square root of x minus 7s we have? We have 2. So we say 2 square root of x minus 7. Hypothetically speaking, let's say if that was a 3 in front of the first radical, then my answer would have been 4 square root of x minus 7, because it would be 3 plus 1. Okay? Any other questions? Look like you had a question. Yeah? Mostly when you have these radicals. Yeah. Mostly when you have the radicals. There's like other different techniques, but with the radicals, the conjugate ways work nicely for us. Okay. Ready for part D?
Yeah.
I'm just going to slide it down so I can start writing out part D. Let me just slide it back up just to see what part D was. Okay, k of x equals 3 over x plus 4. All right, so in part D, our function is k of x equals 3 over x plus 4. So as you've seen in the first three examples, oh, sorry, x plus 4. My bad, that's an h. Oopsie. As you've seen in the first three examples, the first thing that you would like to do is compute x plus h, or namely k of x plus h. So k of x plus h means that wherever I see an x, I just replace it with x plus h. So this will give us 3 over x plus h plus 4. All right, now we apply our limit definition of a derivative. We say the limit as, or sorry, we can say k prime of x is equal to the limit as h approaches 0 of 3 over x plus h plus 4 minus 3 over x plus 4, all divided by an h. Now, here's the trick or the technique for this one. If you look at what comes after your limit statement, you can realize this is a complex rational expression, right? Because if you look at your numerator contains fractions. So how do we simplify this? Well, in pre-calculus, one way that you learn to simplify it is by the LCD technique. Essentially, what you're going to do is find LCD of the complex denominators. So the complex denominators are going to be x plus h plus 4 and x plus 4. Essentially, because there's this plus h in between the x plus 4, it makes these two terms essentially prime of each other. And since they make it prime of each other, your LCD is just simply the product of the two, right? So your LCD of x plus h plus 4 and x plus 4 is the product of it. So it's x plus 4 times x plus h plus 4. Now, here's what we're going to do. We're going to take the LCD and we're going to multiply it by 3 over x plus h plus 4. Then we're going to take the LCD multiplied by 3 over x plus 4, and then we multiply it by h. All right? So in my second line, I write the following. I say the limit as h approaches 0 of x plus 4 times x plus h plus 4 times 3 over x plus h plus 4 minus 3 over x plus 4. And again, we're multiplying it by the LCD. All divided by h times x plus 4 times x plus h plus 4. Uh-oh, what happened to my video? I gotta restart the recording. Well, not the recording. I don't know why this happened. Sorry. Okay. It should be good again. All right. Good things happen, by the way. The LCD helps us clear complex fractions. So, for example, when I took the LCD and I'm going to multiply it by 3 over x plus h plus 4, since we have an x plus h plus 4 in the numerator and denominator, they will cancel out. So this will give us 3 times x plus 4. And then in the second term, 3 over x plus 4, when you multiply by your LCD, the x plus 4s will cancel. That will leave us with negative 3 times x plus h plus 4, all divided by your denominator of h times x plus 4 times x plus h plus 4. And the denominator, you can leave it alone for the moment. All right, now what I need to do is try to simplify this numerator. So what I can do is distribute the 3 inside the first set of parentheses, and I can distribute the negative 3 inside the second set of parentheses. This will give us the limit as h approaches 0 of 3x plus 12 minus 3x minus 3h minus 12, all divided by h times x plus 4 times x plus h plus 4. Now let's look at your numerator. Things can cancel out. We can cancel out the 3x, we can cancel out the 12s, and you will have a negative 3h on the top. Because you have a negative 3h on the top and an h on the bottom, the h can also cancel out as long as h is not equal to 0. Okay, so as long as h is not equal to 0, we're going to get the limit as h approaches 0 of negative 3 over x plus 4 times x plus h plus 4. Now, as h approaches 0, we know that goes away. We'll have negative 3 on top, x plus 4 times x plus 4 on the bottom. And how many copies of x plus 4 do we have? 2. But you can't say 2 times x plus 4, but rather x plus 4 squared. Right, so you can rewrite your derivative as simply negative 3 over, so there's no 6 there, that was just the slide number, of x plus 4 squared. That would be your derivative of k of x, k prime x. All right, let me just stop this recording and then I'll entertain some questions.